if you came to the session yesterday, we looked at the IoT for Beginners curriculum that we at Microsoft have produced. The purpose of today is to basically have an open discussion around everything we looked at yesterday. So it's kind of very much an Ask Me Anything. I've got a few things I want to work through to show off how to use a Raspberry Pi and use the virtual IoT device that we talked about in yesterday's session. But otherwise, this is very much an open conversation. So there was a few kind of homework bits yesterday. We can bring those up and talk about those if you want to. Otherwise, any questions you've got, I'm here to help. I'm here to answer. So you can either use the raised hand thing if you want to actually ask a question, and then turn on your mic and actually ask the question. If not, feel free to put the question in the chat, and I will obviously read out the question, and then we'll answer it. Maybe discover some answers together. So this should be a bit of fun session. Should be very interactive, and just will re-emphasize the code of conduct. In yesterday's session, it was very much you couldn't come off mute, you couldn't say anything. This one, please obey the code of conduct. And it's not just you, it could be people around you. So if you leave your microphone unmuted and there's somebody in the background who says something that breaches our code of conduct, we will obviously have to remove you. So just be conscious of who's around you as well if you turn your microphone off. Awesome. I can hear somebody's got their microphone on. That's not me. So don't know if we can control that. Yep. Ed, hello, welcome. You've got your microphone on. I'm just going to mute you. Thank you very much. Brilliant. Thanks. Cool. So just by way of introduction. So as said, I'm an education head advocate at Microsoft. So it's my job to help folks in the education space be successful with Microsoft technologies. So if you are a teacher, bootcamp instructor, a student, anybody who wants to learn Microsoft technologies, I'm here to help you. My particular area of expertise is the Internet of Things, using Azure AI services and our various Microsoft IoT services. So that's kind of, if you've got any questions on that, I'm here to help. I'm all over the internet at Jim Bob Bennett, Twitter, GitHub, Instagram, LinkedIn. So feel free to connect, reach out, message me, ask me questions. And if there's anything I can help you with, if you're a teacher, you want to bring IoT into the classroom, maybe using this curriculum we've built, or if you're a student, you're doing a capstone project with IoT, you want some help, anything like that, please get in touch. I'm here to help you. And if you've also got horror stories about how you've hit problems with our tools, how things haven't worked for you, again, I would love to know, because we want to make sure that the Microsoft ecosystem is the best experience for you. So if you've had a bad experience, I'd also would love to know so we can help improve things for you. So we'll say all over the internet, Jim Bob Bennett, please feel free to connect. I'm quite a friendly chap, so I never say no to people messaging me. So this is the link. So this office hours is based off yesterday's lesson 1 from IoT for Beginners, the 24 lesson curriculum that we've put together to introduce IoT. This is the link to that, aka.ms/IoT-beginners. Should appear in the chat as well, hopefully some point soon. So if you go to this link, it'll take you to our curriculum, which is up on GitHub. It's fully open source. It's completely free. 24 lessons that cover the journey of food from farm to table with the help of IoT. So we start off by just introducing IoT, lighting an LED. These are the 4 lessons that we're doing as part of the series. We then look at the IoT for digital agriculture with plant monitoring for growth, soil moisture monitoring and automation of soil moisture. We then look at logistics and transport, how you can track location, visualize that on maps, and then use geofences to get alerts when a vehicle enters or leaves a certain area. We then move to AI on IoT and look at fruit quality detection, kind of factory processing, quality assurance, and how you can use IoT devices with cameras to look at something and work out whether it's good fruit or bad fruit, and then we actually run that on the edge, actually have the AI models running on IoT devices. We then look at retail. That's object detection for shelves to make sure you've got all the things on the shelves that you should have on the shelves, and if not, get alerts. And then finally, we look at the consumer endpoint of food, which is where you cook it. And one of the biggest uses of consumer IoT in the cooking space is setting a timer. Pretty much most of the usage of the Alexa I've got at home and Alexa some of my friends have got is setting timers when cooking. So you actually get to build a timer to help you with cooking. So that's IoT for Beginners. So we introduced this yesterday. We talked through the first lesson in depth yesterday, and if you go back to the series page for this particular series, at some point the video for yesterday will be available if you want to catch up on that. So say today is all about an Ask Me Anything, open questions. We can kind of talk through anything that was covered yesterday. We can talk through how you might want to use this in the classroom. We can literally talk through anything. Yes, so it's open, it's free, we have no agenda. So at any point, as I say, stick your hand up or stick a question in the chat. But I will kick off with, one thing I will kick off with is a shout out to our good friends at Seed Studio. Now, IoT, the T in IoT is things, this is hardware. And so to be successful with Internet of Things, you need hardware. Now, we've actually built the Internet thing, the introduction to, we've built IT for beginners so that you don't necessarily have to have hardware. We have a virtual solution, which I'll be going through in a minute, to allow you not to have to buy any hardware. But if you do want to buy it, we've partnered with Seed to make it easy to buy the hardware. This link here, ak.ms/IoT-beginners kit, this will take you to a page on Seed Studio's website where you can actually buy the kit that we use for this particular curriculum. So let me just bring it up. So you've got a Wio terminal-based kit, which is Arduino-based, or a Raspberry Pi-based kit. So you can literally click on it and buy the whole kit, as many sets as you need. So if you just want one for yourself to play with, or you want 20, 50 for your classroom, this is a kind of one-click way to buy it. It just saves having to go and pick 30 of this sense from 30 of that sense from 30 of the other. So Seed have kind of helped us make it easy to buy this hardware, which is pretty cool of them. So big shout out to Seed if you want to get hold of this hardware. Okay, so I did say yesterday that what I was going to do, one thing I was going to do today is go through getting set up with a Raspberry Pi and getting set up with a virtual IoT hardware. So while you think of any questions that you want to ask, let me just dive into that now and kind of show you how you can get going with those devices. And I'm going to start with the Raspberry Pi. So for those who weren't in yesterday's session, if you've not come across the Raspberry Pi before, you're missing out. It is epically good, absolutely epically good. It's a British designed, big shout out to the Brits because I'm one. It's a British designed computer that was designed originally to help kids learn how to code. And so they put together a relatively low cost computer that runs a full version of Linux. So this is a fully featured computer. This is the latest iteration, the Raspberry Pi 4. Now this is a beast of a machine. It's pretty small, compared to my hand. I'm not a large chap, so it's pretty small if you look at it compared to my hand. It's got a quad-core 1.5 gigahertz processor. This one's got 4 gigs of RAM in it. You can get them up to 8 gigs if you want to. It's got an SD card slot for storage. Lose my view there. For storage. It's got USB ports, Ethernet port, a special socket for adding a camera, a special socket for adding a display if you want to, but it's also got dual HDMI outputs, so you can run 2 screens at 60 frames per second, microphone output, powered by USB-C, and it's got a line of pins here that you can use to attach sensors, any kind of other devices. Now, the original ones of these were designed for kids to learn to code with Python or Scratch. And over the past 10, 15 years, whatever it is, they've got more advanced, they've got more powerful. And this is a beast of a machine. And this particular one, I'm not sure how much the 4 gig version is, but the 2 gig version, I last checked, was $35 US. So they're not ridiculously expensive. This is substantially cheaper than any other full featured computer that you would buy. And you just plug in to HDMI to a monitor, you plug in keyboard, mouse, and you've got a fully featured Linux computer. They're really, really great for kids to learn to code, but also great for IoT. These GPIO pins, general purpose input output pins, dive into this more tomorrow's lesson, but this allows you to plug in not just components, LEDs, resistors, and that kind of stuff, but there's a whole massive ecosystem that you can plug into those pins of pre-built hardware. So for example, the Seed stuff I was talking about earlier, this is a little hat. See the little rack here? This just slides onto those pins, and you've got a board with sockets in there for the Grove ecosystem hardware. So there's a whole load of different versions of this. Now this is the standard Pi. If 35 bucks is too expensive for your needs, then how about 10 bucks? Raspberry Pi Zero. Bit less powerful, only half a gig of RAM, but this is $10. $5 if you don't want Wi-Fi. And this, again, it's got HDMI out, it's got USB, plug-in keyboard, mouse, plug in an SD card. You've got little holes here you can solder some pins in. In fact, here's one with the pins actually soldered in. And so you're looking at $5, $10 for a small computer. Pretty cool. And then if you want to go further, if you're feeling a bit flush, and if you're like me, you grew up with the all-in-one keyboard computers like the ZX Spectrum or the Commodore 64, this is the Raspberry Pi 400. So this is a Raspberry Pi 4, same as that, but it's inside a case with a keyboard. You literally just plug in a mouse, HDMI, there's the GPIO pins if you want it, and you've got an all-in-one computer. This is an excellent, excellent device. If you've got kids who need a computer, this is great. It's about $100, comes with a mouse, you plug this into your TV, hey presto, you've got a fully featured computer, connects your TV to code. I'm a big fan of Raspberry Pis, absolutely a big fan of Raspberry Pis if you hadn't noticed this already. As I said, they are full Linux computers. So here I have a VNC connection to that particular Pi, and it's running Raspberry Pi OS, which is a version of Debian Linux. So anything you can do on Linux, you can do on a Raspberry Pi. It's got an ARM processor, so you are limited to applications that run on ARM, but there's a whole lot of ARM support for Linux, so it's pretty cool. Now, to use this for IoT, I've been focusing on Visual Studio Code. So that's the coding environment I've been using across the whole IoT for Beginners curriculum. Yesterday, we looked at using VS Code with Platform IO to do microcontroller development, but you can also use it on your Raspberry Pi, which is pretty cool. And there's two options for running it on the Pi. So the first option is you actually run it on the Pi. So when you install Raspberry Pi OS, you can install a full version of Raspberry Pi OS, which has got the full window manager, it's got the whole UI experience that you would get when you plug this into a TV or a monitor. And it comes with some built-in programming tools, a web browser, media player. It used to come with a version of Minecraft, but I think they've removed that now. But it comes with the basic tools you can use, and you can then install whatever Linux applications you want. Now, I love VS Code, and recently we released a version of VS Code that supports the Raspberry Pi. And you can literally install it, sudo apt install code, and that will go off. I've already got the latest version, yay. So that will go off and install Visual Studio Code on your Raspberry Pi. If you've not used VS Code before, it is a free, almost completely open source development text editor. Now, when I say almost completely open source, the whole core of it is open source. You can build it fully open source and you can run it fully open source. The version that we distribute at Microsoft has a few copyright things in there, such as the logo. Yeah, obviously, all the Microsoft brand logos, trademarks are kept copyright, so those are not open source. And we do have a small amount of telemetry in there, which we use to simply track what features the application are used. We don't track individuals, we don't care about individuals, we just want to see, are people using these features? Standard product management ideology. We track what's being used so we can work out what to improve. We track crashes, we track errors. If you don't want any telemetry, you can completely switch that off, or you can build from source if you want to. So I do sudo apt install code. That then puts code in the programming thing. Click on that, and I've got Visual Studio Code running on my Pi, which is pretty cool. Now, Visual Studio Code works on extensions. So out of the box, it doesn't support Python, and Python is the most popular programming language for doing IoT on a Raspberry Pi. But what I can do is I can install a Python extension. So we have a Python extension that contains what's called a language server that allows it to recognize the Python language and provide IntelliSense and refactoring and code formatting and stuff like that. We've got bits and pieces for running Jupyter notebooks. If you've done data science Jupyter notebooks, you can run those with the Python extension, and kind of a whole lot of other capabilities that makes Python work. And then I can write Python code that runs on my Raspberry Pi. So what I could do, I could go here, let's create a new file. And then, yeah, I could do print, got all my IntelliSense. Yeah, all the things that need some IntelliSense. There we go. I can run that, and we all work. So VS Code is running on the device. Now, if I wanted to do some IoT on here, Yeah, I'll just show a quick study demo. Just lighting an LED, nothing too flash. We'll do more. We'll do more on the Pi tomorrow as we work through the lesson. But if I plug in an LED to some of these pins, so it's an LED. Got a resistor here. Top tip: if you're ever using LEDs, put a resistor in place because otherwise you'll burn it out. This is why, so if you look in yesterday's lesson when we talked about this, I talked about how we're using the Grove ecosystem for all of this rather than using raw components, because I don't want people to blow up LEDs. I don't want people to have to learn to solder and hard stuff like that. I'm just showing this just for a bit of fun. So I've got an LED there with a resistor so we don't burn it out, connected to the Pi. The LED is not lit, but I can write a bit of code. Got a bit of code here that sets up my GPIO pins, sets up a particular pin. Pin 17, not 18. Let's just put it on the right pin. Sets up a pin to send electricity out to the LED. Waits for a bit, turns off the power. So assuming this all works, if I go back to my camera, what you'll see is the LEDs lighting on and off. So I've just written a little bit of an IoT application with VS Code on a Raspberry Pi. So that's one way I can code with a Pi, is by actually connecting to the Pi, connecting it to a monitor, keyboard, mouse, or connecting via VNC and coding on it. Now, another option with the Raspberry Pi is you go headless. And the idea behind headless is you install a version of the Raspberry Pi OS that doesn't have the window manager, doesn't have the UI side of it. It's just simply a terminal. Now, the advantage of doing that is it takes up a lot less space. It's a lot faster to boot up. And if you need to do things like anything that you rely on power, when it's running in the terminal mode, it's using less power than it is here to kind of simulate to run a window manager. And so that's called Raspberry Pi OS Lite. And so under the hood, it's kind of the same. You just don't have all the window capabilities. And if you put that on a Pi and you want to code it, well, that's where it gets a bit more tricky. You could connect the Pi to a monitor and you just get a raw terminal, and then it's kind of Nano or Vim or Emacs and all that. But I don't want to do that. But instead, what you can do with VS Code, another big shout out to VS Code, is you can do remote development over SSH. So as long as you've got SSH, Secure Shell, running on your Pi, which is pretty easy to switch on when you set up your Pi, you can connect from VS Code running locally. So there's this remote SSH extension, and it allows you to connect to a device and you run as if you're on that device. You can open a folder, you can access the files in that folder, you can debug, you literally do everything as if you were running locally, except all your code runs on the remote device. So what I can do is I can connect my current window to that particular Pi. So this will now go off. It'll make an SSH connection to the Pi, install a little bit of software that makes it kind of all work, and then I'll be connected to the Pi. If I bring up the VS Code terminal, it'll be a terminal on the Pi. If I open a file, it'll be the file on the Pi. If I debug, it runs the actual debug session on the Pi, which is pretty cool. What would really help is if I actually put the right IP address in here. Pi at 192.168.197.212. Let's try that again with the right IP address. Things work better with the right IP address. Okay, so here I am connected to the Pi. You see my terminal, Pi at Raspberry Pi, so that's my Pi. You've got my hello.py and app.py, hello.py, app.py, same files as those. I can open a folder. I'm just going to open, again, this is on my Pi/home/Pi. Open that, give that a second to refresh. So it's Pi on this, all these files here, same as all these files here. So it's as if I'm running locally, but this is VS Code, it's running on my Mac. And if I bring up the app.py, exactly the same code. Now what I can do with this remote connection, I can also install extensions. So if I want to install the Python extension, I've got this install on SSH. I click this, this will actually install the Python extension in the remote session. So any extensions I have installed locally when I run VS Code locally are not available in a remote session. It kind of keeps them all isolated because they may not be applicable to a remote session. But when I do have set up a remote session, I can then install the extensions I want. So I can install the Python extension. So that way I get all the language understanding. Because at the moment, without that, if I bring up the app.py, it colors a few words by guessing, but I don't have any of the nice full syntax highlighting IntelliSense and all that. But once it's installed, I better debug this code, run up the Pi, and you'll see the LED light up. So let's give that a second to, oh, reload required. Just reload the window. Give this a few seconds. Yep. So now load the Python extension. Once we select my Python interpreter, because obviously there's more than one, so you choose the one you want. Go for the default one, which is Python 3. And then now it's got all my IntelliSense and everything ready to go. So I can come in here and I can stick a breakpoint on there. I can debug the local file. Well, select my Python interpreter. There we go. So this is now running. This is debugging the code on my Pi. So if I set the LED to high, go back to my camera, there's my LED on. Sleep for 1 second, set it to low, my LED's off. So VS Code is running on my Mac and I'm remotely connected to my Pi, which is really, really useful. It means if you've got a setup with a Raspberry Pi in it that's connected to a lot of hardware that's managing something, you don't have to worry too much about going to the device, plugging it into a monitor, keyboard and mouse, and actually debugging your code. Or you don't have to worry about using things like Vim, Nano, Emacs if you don't want to. And I use this a lot. So for example, if you probably see on my camera, I've got some nice pink lights behind me. And this is all IoT powered. I've got a little Stream Deck on my desk where I can change it. It's orange, I can go multicolored, back to pink, a few different color combinations. And this is all powered by a Raspberry Pi Zero. So this is powered by one of these tiny little Raspberry Pis that is fixed underneath the bottom shelf. So if I want to add a new color combination, I can then connect to it remotely and change the color, which is pretty cool. It's pretty cool. So let's just exit that session. Let's close VS Code. So that's how we get started on a Raspberry Pi. The other thing I did want to show off today is how to get started with the virtual IoT device. Now, as I said, this is all Q&A, so if you've got any questions, feel free to put questions in the chat. Feel free to put your hand up. More than happy to kind of answer anything absolutely at any point. So when I'm going through anything, ask me any questions. If there's something that's a burning question you want to ask, just jump in and let's talk about it. So let's talk about the virtual IoT device we've got. So I've got a little project here called Counterfeit. And this is a project that simulates IoT devices. So the idea behind this is we don't want people to have to buy hardware if they don't want to. Yeah, it's $100 is not much to me as a highly privileged white man in the tech sector in the US. But $100 can be a lot to a lot of people, especially to academic institutions which are desperately underfunded, especially in some places where they're more interested in their hedge funds than they are actually for providing funding for students. So we wanted to put together a way that you could actually do IoT devices without actually having IoT devices. And so let's actually do it. Let's actually do a quick demo of what this tool is. So it's a Python application. You install it locally, you run it locally, and then you use this to define the sensors that you want, and you access those sensors. So I'm just gonna create it. Come on, terminal. So I'm just going to create a folder. So let's just open that up here. So just open up a folder on my desktop. create a Python file here, just to load the Python extension. I'm going to create a Python virtual environment. It's always good practice to have a virtual environment to install all your stuff in. So create a virtual environment, and then let's just make sure that virtual environment is set. No, it's not finding it. It's desperate to find my mini forge one. Okay. Come on. Okay, it's playing out today. It does not want to find my virtual environment. Oh, there we go. It took a few seconds. So I've got a virtual environment, and then what I do is I pip install counterfeit. And this installs the main application for counterfeit. So that's gives a second to install. This installs a web app that I can then run locally, and from this web app I can define the hardware that I want to have. Now, once I've defined the hardware, I need to actually call into that hardware. And what we've done is we've created what we call Shims, and these are fake versions of well-known IoT libraries. So for example, if you want to access a serial connection from your Raspberry Pi to talk to a sensor that sends data over a serial connection, you use PiSerial. We've got a version of PiSerial that you can install. The API is the same as PiSerial, but instead of actually reading from the serial port, it reads from any serial sensors that you define inside counterfeit. Pi camera. The Raspberry Pi has a official camera module, which is, where is it? Here we go. Has an official, so there's a Raspberry Pi. Rearrange my screens because VNC doesn't like changing screens. So this is the Raspberry Pi camera module. It's an official one by Raspberry Pi, hence the logo. Got a ribbon cable, plugs into a camera socket here. The Pi camera Python library is the library you would use to access that. We've got a version of Pi camera that talks to counterfeit to access your webcam. The Grove hardware we use for this, we've got versions of some of the Grove sensors, so you can install the Grove, a Grove shim, and make calls as if you're calling the Grove hardware, but again, it calls the virtual hardware. So give this a few seconds to do that. And while it's doing that, just install some of the shims. Hope I can spell. There we go. Ah. Good fun thing with pip is sometimes things don't work until you upgrade pip. So let me just upgrade pip. There we go, done. Cool, so that's all installed now. So to run counterfeit, now once it's installed, it just becomes a global command you can run anywhere. So run counterfeit, and that will run locally on port 5000. So if I go to here, go to localhost port 5000. This is counterfeit. So here, I can create fake hardware. So question from Nerdjar. So from what I understand, I can create a fake Raspberry Pi from the virtual counterfeit app and use the same APIs and modules to talk to the virtual device we created. So it's not so much creating a fake Raspberry Pi. So Raspberry Pi is a full Linux computer, and that was running Python code. But then when you connect to sensors, you would use a sensor library that will then talk to a sensor. So you would write code to use, say, the Pi camera library, and that would talk to the Raspberry Pi camera, grab a picture, and make that available to Python code. So what you would do here is, rather than creating a fake Raspberry Pi as such, is you would write Python code, and your Python code would look almost identical to the same Python code you would write on the Raspberry Pi, but it would access a virtual sensor to finding counterfeit rather than the real one. So if we just do I mean, as an example, I can say I want to find a camera. I'll call this one Pi camera, and then this is my camera. So I can choose in this camera what image source I want to do. So when I use my Pi camera code and say, give me an image, I can choose what the image is. I can choose a file. So if I always want a static file to come back every time, I can do that. Or I can connect it to a webcam. And if I connect it to, say, a different camera, my camera over there. So that's now set up so it's accessing a camera on my Mac over here rather than the camera I'm using at the moment. And so what I can then use the Pi camera code to access that. So, oh. I'm just going to try and bring up this. Let's close that one down. It's automatically ended up there. It's all in here. So what I can do is, I mean, let's grab a bit of code from somewhere. So let's grab some code here. So here's a bit of example code that would talk to the Pi camera. Now, if I was writing this on a Raspberry Pi, my code would be almost identical. So kind of the first difference here is I have a couple lines of code here that connects to Counterfeit running locally. So this sets up a kind of global connection to Counterfeit. It's running on localhost and port 5000, but I could actually run this anywhere. So I could have Counterfeit running on one machine and then access it from a different machine. Yeah, I could, if I got a Raspberry Pi but no sensors, I could run my code on the Raspberry Pi, talk to Counterfeit running on my Mac, for example. So just set up a connection, and then when I import, if I was using the Pi camera on a Raspberry Pi, my code would be this, from Pi camera, import Pi camera. The difference we're doing here is we're saying from Counterfeit Shims Pi camera. So it's just using a alternative package that we bring in. Other than that, the code is identical. So I create a Pi camera, I set the resolution, the rotation. Hey, Lana, hello. You're off mute. Do you have a question? Or... No. Ah, awesome. Muted now. Thank you very much. So this is identical to what I'd run on a Raspberry Pi, and this is going to use the camera, set the resolution, set the rotation, and then capture the image from the camera. And here it's just going to write that image out to a file. So if I just go to a different terminal and I go Pi run this, it's going to work. Come on. Ooh. Did I actually set that? Yeah, that's all set. Let me just try that again. So bear with me a second. I made a boo-boo because it should be. I named my sensor wrong. I need a camera called Pi camera. There we go. Set that. There we go. Cool. Now I'll do that. And there we go. Smart for the camera. And there we go. So it's captured the image. So if I was writing this on a Raspberry Pi, I would be using, let's say I'll be using this Raspberry Pi camera module, comes on a ribbon cable, plugs into that socket on the board there, and the code would be almost identical. It would be literally that. We don't need the connection, and we have a different library. Otherwise, it's exactly the same. So We support a number of different bits of hardware with this. We support all the hardware that you'd use in IoT for beginners is supported through this, plus some other hardware. And this is kind of a new open source project I've been working on. So if you want to use this for other hardware and we don't have a library for it, then please raise an issue. We can work together on actually getting that support in place. This is kind of designed so that I can do everything that I could do with the real hardware for this course, just without actually having to spend any money at all. I just can run this on my local machine. So that's kind of what that counterfeit was all about. So another question in the chat. Josiah said, I'm sorry I missed the very beginning. Is Python the primary language for IoT? Yes and no. It's a fantastic question. So what we looked at in yesterday's lesson, I don't know if you're here for yesterday's lesson, we looked at two different IoT ecosystems. You have Arduino and you have single board computers. Well, so you have microcontrollers and you have single board computers. So microcontrollers are small, low-power devices. Clear my desk. So a microcontroller is, something like this $2 Raspberry Pi Pico, tiny little device in there, or like a $5 Arduino Nano. They are low-powered hardware. They run, in the megahertz. They have kilobytes of memory, maybe if you're lucky, a megabyte memory. So they're very low-powered devices. We'll go more on these in tomorrow's lesson. But so the microcontrollers, very low powered, very low memory, and you would traditionally code those in C or C++. There are Python variants available for microcontrollers. MicroPython and CircuitPython are two great examples. So you can write Python that compiles down to low-level code. But a lot of what you would do with microcontrollers, like ESP32s and all these kind of small devices, you would do this in C or C++ in general. So the other option for IoT devices are the more powerful single board computers. So these are the devices like the Raspberry Pi that are fully featured computers. They run a full operating system and you can code in any language that works for the operating system. So if you want to code in Python, you can. You want to code in C#, Go, Rust, JavaScript, whatever language you want, you can code in those languages. The Raspberry Pi here, this supports Linux. So any programming language that runs on Linux, you can run on a Raspberry Pi. Now, Python has become the most popular programming language for IoT devices on the Raspberry Pi simply because of the maker community. So there are a whole load of makers out there who are putting together kits, light up clothing, weird machines that wave, Lego sorters, Rubik's Cube solvers, a whole raft of different devices. And a lot of them use Python because it's quite an accessible language to get started with. In terms of the hardware suppliers, if you go and buy like this Grove kit, for example, this is all easy to use sensors. And by easy to use, I mean this LED has no wiring apart from just you plug this into the socket. I haven't get the right round. That's how you wire an LED. It's kind of easy to use like that. And they have programming environments for this, which supports Arduino in C and C++, or Python on a Raspberry Pi. They don't have a Go version of this or a Java version of this. So a lot of the ecosystem things you buy, a lot of the hardware you buy has Python libraries. I mean, here, for example, is a strip of lights. The blinked lights from Pimoroni, a UK-based company that makes hardware for makers. Library for this, all in Python. So it's kind of become, because everybody uses Python, everybody uses Python. So Python is the more powerful language for IoT. When it comes to connecting to the cloud, all the cloud providers have Python libraries. So for example, for Azure IoT, we have Python libraries you can use to connect. So kind of Python has become sort of the standard language for this. So yes, for Raspberry Pis, Python is the primary language. In terms of microcontrollers, as I said, you can use Python. There's CircuitPython, and there's a company called Adafruit who do amazing devices. In fact, one second. I have way too much hardware. So Adafruit, for example, will do things like this. This is called a Pi Portal. So it is a microcontroller, screen, SD card slot, sockets to plug in other hardware. This is designed to run CircuitPython, so a version of Python that compiles down for microcontrollers. And Adafruit have a whole range of these Python-based, Circuit Python-based board. So that's a Pi portal. This is a Pi badge with a camera module attached, and this has got a screen and buttons, and you can run games on here. So you want to code this up to play Pac-Man or something, you can do all that in Python. So there's kind of a whole ecosystem based around microcontrollers in Python if you want it. So definitely Python is the most popular one. If you are building professional IoT systems that you want to run on microcontrollers that live inside big machines or consumer devices, then you probably would be custom hardware done in C and C++, just because that reduces the power requirements. It makes it faster. It can be much more efficient with memory. On a constrained device, if you write it in Python, you might be using 3-4 times the memory if you write it in C++, and that larger memory chip might be 50 cents a device, which multiplied by a million devices is quite a substantial cost. So yeah, for hobbyists, Python is definitely the way to go, and people learning Python is the way to go. Can we code in C# for the virtual environment? No, we don't have any C# support for counterfeits or Python, because that's where all the libraries are. We don't have any C# support in this IoT for Beginners curriculum at all. Some folks have asked for it, but Python is the most popular language. For students coming new to IoT, Python is one of the most accessible languages there. So no, we don't have C# for a virtual environment. So Josiah, yep, awesome. Glad that was useful. So yeah, those are kind of the two things I really want to show off: how to get going with the Raspberry Pi, how to get going with Counterfeit, the kind of virtual IoT device. And we'll dive more into these over the next few lessons, and we'll actually do more with it and start putting together a few basic projects. But now, really, I'm going to turn this over to you. So, this is very much an Ask Me Anything session. We've got plenty of time left, so hit me with your questions. What do you want to know? What can I help you with? And if not, I'll start asking you some of the assignment questions from yesterday. How would you recommend getting into IoT? Should someone just start a project, or is the book that you can recommend? Funny you should ask that. I would recommend the IoT for Beginners curriculum that's just been released from Microsoft, because that's the theme of all these particular sessions. So yeah, if you weren't here for yesterday's one, or you missed kind of the start of this, IoT for Beginners is a 24-lesson curriculum all about IoT basics, and we released this last Friday, and it's designed for complete beginners. So if you want to go down the Arduino route, you do need some C, C++ knowledge. If you want to go down the Raspberry Pi or virtual hardware route, you do need you need to be able to at least read some Python. And if you have never done Python before, we've got some links somewhere here, some links to some Python lessons that start from the basics. But you can pretty much copy and paste the code if you want to, and just see it in action if you're not too worried about how it works. But this is designed to teach you from the basics. So the first 4 lessons that we're covering in these sessions over this week and next week, we start with just like, what does IoT mean? What are IoT applications? What's kind of the hardware, the dev kits you might play with? What are sensors and actuators? So we kind of have all the content there just to kind of get you going with the real basics. We start thinking about connectivity to the cloud via MQTT, just basic messages going back and forward. And then we actually bring in a load of projects that kind of build on that, so you can actually see IoT in use for predicting plant growth or automatic soil watering, tracking vehicles, visualizing data, AI on the edge to do fruit quality and to find missing stock on shelves, and then consumer devices, voice control timers, that kind of thing. And this is all, so it's all done to teach IoT the basics. Yes, this is from Microsoft. So obviously when we do get into the cloud, we use Azure, the Microsoft platform, but we don't start really getting into the cloud until lesson 8. And we'd use Azure as a way of teaching the principles. This is very much principles first, not Azure first. We've got lots of great content. If you specifically want to learn something about Azure, we have Microsoft Learn, which is full of detailed things for each Azure service. This is all about the basic principles. You then kind of go on to learn Azure at a later date if you want to. And we're trying to keep this as low cost as possible. So virtual hardware all the way through if you want to. And in terms of the Azure services, some of them are completely free. Some of them might cost a few dollars. As long as you spin the service down as soon as you're finished with it, you can do the whole thing for probably less than $1, which is pretty cool. And what is the name of the repo? If you go to, let me just, You know, it's so short, you've typed it so many times, it's probably easier to type it than it is to copy and paste it. There's a link to the repo. And so it's all free, it's all open source. So there is literally no cost, no comments behind this. You can take this, if you're a teacher, you can just take this and stick it in your LMS if you want to. We are working on LMS common cartridge. So if you want to bring this into Moodle or Blackboard, you can do that. But yeah, if you want to fork the repo, make any tweaks to suit your particular pedagogies or the content you need to cover, you can. It's free, it's yours, do what you like with it. Cool, so next question. When's the next session? What is the link? Yep, just the link's in the chat there. Next session is tomorrow. So tomorrow we're going to go through lesson 2, which is kind of a deeper dive. And then we'll kind of dive more into, I'll show you lesson 2. So we're going to kind of dive deeper into what makes up a IoT application. We'll look at some of the different parts of it, security and things like that. We're going to talk a bit about microcontrollers in depth, think a bit about the actual components behind it, the CPU behind it, dive more into single board computers, real-time operating systems, you know, a whole lot of kind of different stuff, kind of going a bit deeper into how the hardware works. Not going to go too deep. You don't need to be an electrical engineer. You know, I don't want to scare people off with NAND gates and OR gates and that kind of stuff. Don't do that. We're just going to just talk about how it all works, give you kind of a better understanding, especially around microcontrollers, because they are incredibly constrained and you kind of need to be aware of these constraints really from the start, because otherwise before you know it, you run out of memory and you don't know and you wonder why your application is not working. Awesome. I'm hearing somebody who's come off mute. Do you have a question?
Oh, yes, I did.
Yes.
So I actually hope to be teaching Internet of Things using Raspberry Pis, all of this. Are there any projects we could take a look at that would get the students started or just, you know, get our imaginations going?
Yeah, certainly. I mean, I'm going to pitch IoT for beginners again. This is all project-based learning. So when we actually talk about the different applications here, these are hands-on projects. So we try to kind of pick one from kind of the biggest areas. And a great way to get started is digital agriculture. So lessons kind of 5 through to 10 are all about digital agriculture. So we start off by using a temperature sensor to measure air temperature, and then we show how you can use that to calculate what's called growing degree days. So every plant grows or needs a certain number of growing degree days to achieve maturity, and these are the number of days, the number of degrees above a minimum for a day that the plant is at. So if it's got a minimum of, say, 10 Celsius, it spends all day at 11 Celsius, that's 1 growing degree day. And then if it spends it at 20 Celsius, that's 10 growing degree days. And you might need like 100 growing degree days before your strawberry plant produces fruit. So we kind of look at that, an actual real world use case, and it's something that students can measure. They can measure temperature and actually use that to follow along with the plant over a period of time. We then look at automatic soil moisture measurement and watering. And so you take a plant, you actually put a soil moisture sensor in the plant, measure the soil moisture, and then use that to control a relay, which you could then connect to a pump if you want to. So you could literally build a full automated soil moisturing system. In fact, one second. I just so happen to have a plant here. So let me just adjust my camera. So what you'd get is you get a soil moisture sensor, one of these. That goes in the plant. That measures the soil moisture. You'd then use various logic to control a relay. So this, you'd turn this on when the soil moisture goes too low, and we explain how the sensor works and the fact that the higher number for the sensor means lower water levels, things like that. And then you can control the relay. That could then be wired to a pump if you want to. I advise doing it without the pump to start with, or at least without water in the pump to start with, because as you're experimenting, it can get quite messy. But then you can use that to water a plant. And if you wanted to kind of build this into a long-term project, you could start with just this. You could then look at how you could scale this up to a whole farm as kind of like a sort of capstone level project. You could look at actually doing this. You do this on lesson 1 as a bit of a fun get going, then you teach the principles, and then at the end you can actually check everyone's plant and see how alive their plant is based off what they're doing for soil moisture measurement. So that's kind of a fun project because everyone loves plants. Everybody loves plants.
This is a classic project for students growing plants, but now this is a next generation.
Yes, automated plant growth. Another good one to do. I mean, the transport projects are GPS based. A little bit harder to get good data because you have to actually take the device places. But if you've got students who would like to go out for a drive or go out for a hike or bike ride or something with a Raspberry Pi connected to a battery, you could plot a map of where they're going and then even set up alerts so that when they come to the classroom, they get you get an email to say, hey, this person's arrived at a classroom. So you could kind of build fun projects like that. Probably another more fun one would be the AI on the Edge project, the fruit quality detector. So this, you train an image classification model. You just use a tool that does it all for you. So you just give it the images and say learn. You don't have to build the AI model yourself. And then you can call this from an IoT device with a camera. The example we use here is just distinguishing between ripe and unripe fruit, but obviously this kind of works for anything really. You can train it on any two, 3, 4, 5 different things, and then you actually run it on an IoT device. So you can have a Raspberry Pi that's not even connected to the internet, and it's got a camera on it, and then you wave something in front of it, and it tells you what that is. Some examples are things like a smart bin. So if you have a bin where you've got recycling and incineration and compost, you could actually train it on the stuff that you sell in your cafeteria. So if you hold up a juice bottle, it will go recycling. If you hold up a banana skin, it goes compost. And you can run all that on the IoT device without it being connected to the cloud. So that's another good fun project that you could build with students.
Yeah, I agree. I think everyone can relate to that one. So
yeah,
very good.
There's so many examples you can come up with this. I mean, the recycling one is again, it's one of those kind of canonical examples that a lot of people come up with. But yeah, you could do it with anything in the classroom, anything that people want to distinguish. So yeah, and all the examples here, we talk you through building all the projects. So, it's a great way to kind of get started with, with some fun projects that are designed for entry-level students. If you want to get more advanced, then we do have, we do have our IoT curriculum resources repo. This has kind of got a set of labs in here. I will drop it in the chat briefly, the link in the chat. This has got a set of labs here where you can do kind of a lot more if you want to build bigger projects. For example, we have a full, call it manufacturing part check. It's based on the same hardware that we're using for the IoT for beginners, but this is you build a virtual assembly line. So you train a model to identify something on an assembly line, whether it's in one piece or not. My example is a Lego Stormtrooper, and it can tell whether it's in one piece or in 2 separate pieces. And you kind of, I use a button here to trigger a camera. So you press a button and it takes a photo and lights green or red, depending on whether it's whether it's good or not. But you could then take this further. You could actually put like a proximity sensor. So as something gets close, it triggers it. You could even build a little conveyor belt if you wanted to take it further, actually build your whole setup. And for example, Purdue University in their Polytechnic Institute that does a lot of IoT work, they've literally built this on a large scale using actual industrial components to build a conveyor belt. They put things on it, it comes along, an industrial camera takes a photograph and kind of runs this model. So again, this is another good fun one to do. Lego is a great way, and you're sponsored by Lego as well. So Lego is a fantastic way to take the little bits of hardware and build it into actual IoT devices, as in actual structure hardware. I mean, this was very simple to build for me. Got it here. Let me just. I mean, this is the whole setup here. It's just one big block of Lego with everything in it. And once you've built one, it's easy to reuse. It's kind of nice to actually have like Lego to build a framework, because otherwise you're holding cameras and waving cameras around. So, so yeah, hopefully that gets you started. Feel free to reach out to me. I'm Bennett on GitHub, LinkedIn, Twitter, whatever. or jim.bennett@microsoft.com. Feel free to reach out if you want any more ideas or anything else I can help you with. It's my job to help educators like you be successful. So anything I do to help, if you want like a guest lecture, things like that, then yeah, let me know and I'll do what I can. Cool. Right. Next question. Can we complete all 8 exercises with the virtual environment? Yes, you can do the whole lot. The whole of IoT beginners from start to finish with Counterfeit. You don't need to buy any hardware if you don't want to. We wanted to make sure that this was accessible to everybody. So absolutely everything you can do without buying any hardware other than the computer that you run it on. Entire IoT ecosystem is evolving very fast. Yes. Are there any best practice design guidelines? What are the combination of devices, libraries, which to be used from design solution standpoint? No, I have yet to find any best practice because it is moving so fast. There's so many new devices that if you say this is the best practice, then by the time you finish saying that, a new device is out and there's a different way. My best practice, as it were, is to go where the ecosystems are. So like the reason we chose Arduino and Raspberry Pi for this is because the ecosystems are massive. Yeah, if you want to get Pi libraries, Pi hardware, yeah, there's a ton of it. I mean, you go on to, Pimoroni, for example. UK-based company, you want Raspberry Pi stuff. I mean, what do you want? You've got all manner of sensors and cameras and ink displays and arcade machines and there's so much stuff you can buy. Books teach you how to use it. There's such a huge ecosystem of lights and robots. I mean, what have I got here? Here, for example, here's a Raspberry Pi in a remote control car. So, yeah, the reason I chose Pi is just because there's a big ecosystem for it. The reason I chose Arduino is because there's a big ecosystem for it. Other than that, it depends on how deep you want to go in terms of how you want to architect your application. So, for example, if you're building a big enterprise application, then, we at Microsoft, we have architecture guides. We have a whole lot of quick starts. Where are we? Not accelerators. That's what we call them, accelerators. Where are we? Come on. So, we have a load of IoT accelerators. So if you want to set up a different thing, we have got, we have got an out-the-box accelerator where you kind of one-click deploy 95% of a particular project. You want industrial IoT, connected factory, things like that. We've got the bulk of the project there. It's kind of a best practice guide. But really, it's down to what are your needs. If you're just playing at home, Raspberry Pi is great. If you're building an industrial device, then you need to research the hardware and make sure it works in the environment that you're in. But yeah, let me just drop this solution accelerators link in the chat. For big projects, yeah, it's a good way to kind of get started with a look at the solution accelerators. But yeah, it depends. Very hard question to answer. And you'll come up with something. You're saying somebody asked about edge computing. You can get AI on the edge and you can deploy to an edge device and it'll be great. But then there's TinyML, which is running AI on microcontrollers. And so by the time you get your edge solution better, you may be better off doing it on TinyML because that's now getting better and better and better and better. So yeah, have a look at things like the solution accelerators based off the solution that you're interested in, and you might get a few ideas. But yeah, I don't know if there isn't like any one best practice because there's so many choices. Do you have a recommendation on how to package all the components an IoT device may have into a unified package for potential deployment of the field? Nope, I don't. I must admit my expertise is on creating beginner content for education use. In terms of packaging it, I wouldn't even know where to start. I'll be totally honest. I wouldn't know where to start. There are experts with PCBs and hardware, but I'm not one of them. So I'm sorry, that's not something I can help with. Yeah, I don't know. The RC cards are a project I really want to start. Yes, These cars are great. So I've got the one I've got is a Sun-Founder Pi car. It's oh hello. They seem to have a new one. Oh, this looks exciting. But these are great. They're run off a Raspberry Pi. They've got a camera on the front. They've got Python libraries to control them. And so you can either just, I mean, they come with like a mobile app you can use to drive it around with one of their samples. But you can just write some Python code to drive it around. I had mine connected to an IoT application. I click go forward, back, capture images from the camera. And they're great. And you can run AI models on them. So if you wanted to build something that would drive around and avoid objects, for example, you could train an AI model, deploy it on there, drive it around. They have an example that comes with it, uses OpenCV to follow a red ball. So you hold kind of red ball in front of the car and kind of move the red ball around and the car follows you, which is pretty epic. And Raspberry Pis, because they've got the USB socket, you can add accelerators. So for example, where are we? I mean, this is on screen. This, for example, is a Coral AI accelerator. So this runs TensorFlow models stupidly fast, and I can plug it in to a USB socket. So I can put this on my Pi car and then get an accelerated AI model running on my Pi car to do a lot more advanced things. You know, my plan is to build a self-driving car one day, and I just haven't got round to it yet because there's way too many other toys. You know, once I get going with a toy, then another toy comes out. But yeah, they're really, really good fun. And it doesn't take much code to get going. You know, the libraries have got the turn left, turn right, go forward, go back, capture an image type API, and they're a fun way to get going. You know, it's one of the things I would have loved to have included this in IoT for beginners, but it's very hard to simulate, and they are very expensive. You know, relatively very expensive. So, yeah, they're great. Awesome. Yep. So Trevor, yes, please reach out. I'm more than happy to help you any way that I can. Cool. And any other questions before we wrap up? I know we're a few minutes over, but any other questions? Going once, going twice. I would start saying Bueller, but I'm not sure how many folks would get that. Just people of my age. Cool. Oh, cool. Would you better then hook up your RC car to a WebSocket to drive from anywhere there's an internet connection? Yes, because it runs on a Raspberry Pi with Wi-Fi. So I've connected mine to an IoT application, and people remotely have moved it forward, backwards, left, and right. So totally, you can do that as long as it's got an internet connection. You can control it. It's just a Python library. So as long as your Raspberry Pi can connect to the internet either via the Wi-Fi on board, or you could put like a 4G SIM card in there if you get like a little 4G adapter, something like that, Wi-Fi hotspot, whatever, you could then use that, and you can totally drive it from anywhere around the world. If you wanted to build, say, a humanitarian disaster type solution, a vehicle you could drive through and actually try and find people, you could put maybe face detection on there and have it just drive around, control it remotely, look for faces, things like that. So there's a lot of great fun projects you can do. But yep, totally, you can drive it from anywhere. Next question. The setup we will need to follow along with the exercise 24 lessons. Reactor sessions over 12 weeks. Okay, so we're not running the reactor sessions over 12 weeks. Okay, we're just doing the first 2 weeks for now, just to see how many people like the sessions being done live. We may run the entire series over 12 weeks from September onwards, depending on how many people come to these sessions. The reason we call it a 12-week curriculum is it's designed to be taught in a 12-week semester. So if you're at a university and you've got a 12-week semester, you normally do 2 hours a week of lessons, 2 hours a week of labs, and that kind of matches up with that. But yes, everything you need to follow along. If you want to work through 24 lessons yourself, you can do it all with Counterfeit, and Visual Studio Code, and you will need an Azure subscription. That's all you need. You can go down the hardware route if you want to, but you don't have to. You can totally do it just using Counterfeit, VS Code, and that's all there. So yeah, but yeah, so if there is interest, then I will be running the entire series from September through to December. And Josiah, yep, you'll attend. Awesome, thank you very much. So that's one down. Anyone else? Let me know, and we'll see whether we're going to do it or not. And then what's that? The question was asked really. Where's the recording from yesterday's session? The recording. The answer's there. It'll be up on the YouTube channel in 24 hours.